Hello. Hello.
স্যার আসুন শুরু করুন স্যার আমি তাহলে শুরু করছি Good morning everyone. On behalf of the Department of Mathematics and IQAC Cell of Sitananda College, Nandigram, I, Dr. Deepanjana Das, extend my warmest welcome to all dignitaries, respected teachers, invited speakers, researchers, paper presenters and students to the International Conference on Contemporary Mathematical Problems, ICCMP 2025. It is a matter of pride for us that scholars across India and abroad have joined us today for an enriching exchange of ideas and knowledge. This two-day conference brings together eminent mathematicians from institutions in India, Czech Republic, Poland, China, Taiwan and beyond. We are here to explore the latest developments in mathematical research, emerging problems, and innovative methodologies. We now begin our inaugural session. For this session, I request our esteemed dignitaries to kindly take their seats on this stage. Already they have taken their seats. I respectfully invited the following distinguished guests, Professor Dr. Shamu Mahali, our Honorable Principal, Sitananda College, our esteemed keynote speaker, Professor Shankar Kumar Roy, and the government governing body member, Professor Dr. Lokhikanto Dolishar. May I request everyone to welcome them with a big round of applause. Today, we begin our conference by celebrating growth, sustainability, and the nurturing of knowledge. Instead of traditional lamp lighting ceremony, we will inaugurate the conference by watering a plant, symbolizing life, learning, and the ever-growing roots of mathematics. May I request our principal sir and our keynote speaker, Dr. Professor Shankar sir and Lokhi sir, to kindly accompany us in the watering the plant as mark of auspicious beginning. এখানটায় ওয়াটার এটা কোথায় জলের এটা সবাই Thank you, respected dignitaries, for this meaningful inauguration. We now move to the felicitation of our honored guest. I request the organizers to kindly felicitate our dignitaries with tokens of respect and gratitude. We are going to felicitate at first our honorable principal, sir. Krishna, come. আচ্ছা আগে প্রিন্সিপাল হ্যাঁ প্রিন্সিপাল স্যার কি নোট সবাই একটু হাততালি দাও এবার স্যারকে দাও স্যারকে পড়িয়েছো চন্দন পড়িয়েছো স্যারকে এই দেখো চো হাততালি দাও সবাই স্যারকে দাও লক্ষ্মী স্যারকে বলো কৃষ্ণ দা স্যারকে গিফটগুলো দাও স্যারের জন্য যেটা স্পেশাল গিফট সেটা দাও এটা দাও সেই স্পেশাল গিফট আনো নিয়ে এসো কৃষ্ণা 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 স্যারকে দাও আমাদের তরফ থেকে। Thank you, everyone. We are delighted that our Honorable Vice Chancellor of Vidyasagar University has kindly sent his good wishes towards this event. I am hereby reading out his message. It is heartening to note that the Department of Mathematics and Internal Quality Assurance Cells of Sitananda College, Nandigram, Purbo Mendipur, are going to jointly organize a two-day international conference on contemporary mathematical problems on November 26th and 27th, 2025, to be held at the college auditorium, the college room 103. I commend this collective endeavor and hope that the deliberation in the conference will really be enriching to all the participants. I extend my greetings and good wishes on the occasion and wish the confluence a great success. Professor Deepak Kumar Kaur, VC, Vidyasagar University. I now request our respected Principal Sir, Professor Dr. Shamu Mahali, to deliver the welcome address. Sir, kind.
Good morning to all distinguished guests. Professor Shankar Kumar Roy, Department of Mathematics, Vidyasagar University. Professor Milan Haldik, CU, Paraguay, Cruz Republic. Professor G.W. Weber, PUT, Punjen, Poland. Dr. Soikot Saha, Department of Mathematics, IIT Roorkee. Dr. Shalil Ghosh, SMS, Beijing, China. Dr. Suman Kumar Das, National Taiwan University of Science and Technology, Chuan. Respected faculty members, eminent researchers, and enthusiastic students, it is my great pleasure and honor to welcome you all to this international conference on contemporary mathematical problems hosted here at Sitananda College, Nandigram on 26th and 27th November 2025. Today we gather not only to share knowledge but to celebrate the spirit of curiosity that derives mathematical discovery. Mathematics has always been an universal language, unity, culture, disciplinary, and ideas. In today rapidly evolving world, mathematical thinking is more crucial than ever. Whatever we are addressing challenges in data science, climate system, climate changes, earthquake, tsunami, artificial intelligence, or pandemic, earthquake, prediction, and mathematical itself present at the very core of the solution. This conference provides a unique platform for scholars, innovators, and young minds to come together and explore cutting-edge problems that shape our global future through keynote talk, research, presentations, and workshops and discussion. We aim to together collaboration and spark now insight that transcend borders. I extend a warm welcome to our international delegates who are from various parts of the world in share their knowledge and expertise. Your participation enriches this event and exemplifies the global nature of mathematical research. I also congratulate the organizing committee convener Dr. Arpan Dhara, Dr. Dipanjana Das, Assistant Professor, Department of Mathematics, and joint convener Dr. Saroj Mandal, HOD, Department of Mathematics, Sitananda College, Nandigram, whose dedication and efforts have made this conference possible to students and emerging researchers. May this event inspire you to push the boundaries of your immigration and pursue mathematical inquiry with passion and preservation. Let us use this day to question, to learn, to collaborate, and to advance our shared understanding of the complex mathematical challenges of our time. Once again, I welcome you all and wish the conference great success. Thank you.
Thank you, sir, for your valuable words for this event. Now I invite Professor Dr. Lukhikanta Doli, sir, the governing body member, to share his words for encouragement. Sir, I invite Dr. Bishwarup Mondal, sir, the member of governing body, to share his words for encouragement.
Thank you for giving me the opportunity to deliver some speech regarding international seminar on contemporary mathematical problems. And I am very pleased to present here. And my distinguished speakers is there. I know him very earlier from the Vidyasagar University. I was the students of Department of Chemistry, sir. Under Bodhe Ranjan, I do my PhD works. So therefore, just few months back, we with the Department of Chemistry also organized an international seminar. So we have some technical problem to bring the seminar in hybrid mode, but today our Department of Physics and Mathematics both joint convention is make it a grand success, and it will be very efficient and for the online participants. So actually this is very much my very tough to discuss about this four things of the seminar field, but I just want to say that it will, I wish the grand success of this seminar, and for this 2 days international seminar, it's the beginning, and I think in future Department of Mathematics and all the departments of our college with the paternity of our honorable principal, much more seminar will be conducted here, and we will get support from the Vidyasagar University and other recognized university in all over the India and abroad also. And finally, I wish to congratulate all the organizers for arranging this type of seminar, and the gathering is very much satisfactory, and I wish all the success of this seminar. Thank you.
Thank you, sir, for your valuable words. Now I go to the keynote introduction. Mathematics does not just solve problems, it creates new words. Today, we are privileged to host such a visionary mind. I am delighted to introduce our keynote speaker, the renowned mathematician, Professor Dr. Shankar Kumar Roy, Vidyasagar University. Professor Shankar Kumar Roy is an eminent professor of Department of Mathematics with Oceanology and Computer Programming, Vidyasagar University. His research area is operation research and optimization. His academic contributions are reflected in multiple publications. He has more than 200 research articles in popular international journals. He guided many PhD students, and also there are many ongoing students under his guidance in PhD program. He has secured a remarkable rank among top 22% scientists in the world in all disciplines in last 5 years. He has been awarded by many international organizations. I am actually very much privileged to welcome Professor Dr. Shankar Kumar Roy because behind this conference, his support and contribution for this event is remarkable. Without his help, nothing will be possible. Thank you so much, sir. Sir, we are honored to have you. I now invite Professor Shankar Kumar Roy to deliver the keynote address. Sir, over to you.
So, good morning to everyone. First of all, a respected principal of this college, Professor Dr. Shamu Mahali, and the member of the governing body, Lokhikanta Doloi Mahashay, and coordinator of IQAC director, Dr. Arpan Dhara, and all the faculties, Dipanjana Das, and HOD Saroj Mondal, and all other faculty members of different disciplines like physics, chemistry, and others, faculty members of this college, and my dear audience. I hope here, those are sitting here, they are the heterogeneous group. That means they are not from mathematics all. What I think, I visited so many colleges and noticed that nowadays the number of students are decreasing, especially in 3 subjects. One is physics, second one chemistry, and the last one is the mathematics. And almost all the colleges, what I noticed that only 1-digit figure for the students, those are admitting in the different colleges. It is really hard to ask how we'll survive in the next days. And I think if this tradition is going on, then government will take the advantage to make a cluster of colleges, and recruitment of the faculty members will also stop. My appeal to all of you, please study these basic subjects like physics, chemistry, mathematics to survive for the next generation. We are here to organize such a big conference or great conference. Actually, I came here 3 months ago for some academic activities, and thereafter I just mentioned this fact to Dipanjana and others faculty members of mathematics, and immediately they replied to me, okay, we can organize a international conference. So I have a good collaborations in different countries, more than 15 countries. I have a collaborator, Europe and South Asia and China and US, so many countries, so many collaborators I have, and several projects also going on this collaboration work. What I want to give here the message in this conference, actually if you learn mathematics, nowadays only mathematics is not enough to develop the society. That means to make the societal development, we need to do some work, it's a multidisciplinary work, by combining mathematics to physics and chemistry. So it is essential to organize frequently such types of international conference to encourage the students of the colleges. It is essential, and I must respect to the principal and others members of this college that they granted to organize such a conference to the mathematics department with the help of IQAC coordinators. I hope in future, others department of science, they will organize a big conference, maybe jointly, as the number of students are continuously decreasing, so jointly they can organize such a conference and offer this platform to the beginners, to the new generations, how we can survive in this struggle community on today's scenarios. With these few words, I must mention here the another speakers means today Professor Milan Hladic. Actually name is Milan, basically from the Bengal, almost all of you know, but I met him during my visit at Czech Republic. He told me that my name is Milan. I mean, you are from West Bengal? So, no. We'll say, you know, this, I told him that Milan is familiar name in West Bengal. And then title is Milan Hladic. He is now the full professor in Department of Mathematics and Physics, Czech Republic, Charles University. Charles University is 300 years old. He will deliver the lecture after my keynote speaker. He is my good collaborator in Czech Republic. Another one, Professor Weber. Weber is now international figure. Means just the nickname of Weber is Willy. Just we type this Willy, then so many friends around the globe and so many collaborators. He knows from India to China to Europe to Asia, Latin America is where. His name, all the scientists are know very well. He is famous. Basically, he did MSc and PhD from mathematics, and thereafter he did PhD in economics also. Nowadays, he is working on the pension fund in Europe also. Means how the government utilize or management the pension fund. Such kinds of activities or the real life problems he is handling and then developing some of the models in such a way that the government can organize the pension fund to all the people who are working in Europe. So with these few words, as we are running late and after my keynote lecture, Professor Milan Hladic will deliver his lecture through online. So based on this thing, I must say, I must concise my speak in a short way. So all of you sitting here to learn the mathematics. Actually, this conference, the name is International Conference on Contemporary Mathematics. At the beginning, I thought that I will deliver a lecture on popular talk. But later I see there are 60 participants. They are all from mathematics. If I say some talk on populars on varieties dimension, then the other people, those are registered and they will present the paper, they can demand that this is not a conference on mathematics. Based on these things, I will say the topic on mathematics, although I will try my best to convince you how mathematics will work for the society. These types of activities can be taken by the help of mathematics. Okay, so I request to all the audience, those are sitting here, please listen my lectures. I realize that somehow the mathematics is so much difficult, but I will say this type of discussions in a lucid way to understand all matters. So with these few words, I must thank to the principal of this college, Dr. Shamu Mohali of the Sitananda College, and the member of the governing body, and all other faculties and the members, those are associated to organize such a great event, as well as the coordinator of IQAC cell, Dr. Arpan Dhara and Dipanjana Das and Saroj Mondal and all others. I did not utter all the names of here, but my respect to all of you, those are involved to organize such a big event. With these few words, I must wish to make a grand success of this 2 days conference. Thank you very much. Okay.
Thank you, sir, for your valuable words for us and basically for the students. Here we have ended our inaugural session. Then we go to our technical session. Sir, I would like to invite you to share your technical session with us. Right now. Okay. 11:30 একদম ডট টাইম ডট টাইম হ্যাঁ
6. আমি ঠিক সময় বন্ধ করে দেবো। No issue. ঠিক আছে। ঠিক আছে। Actually, just I am giving the little bit introduction about on Bengali. Then I can shift whole things in English also. এই যে টকটা আমি বলতে চাইছি, এটার মেন উদ্দেশ্যটা একটু বলে দেই, তাহলে বুঝতে সুবিধা হবে। আমরা সবাই তো এখন স্মার্টফোনে অভ্যস্ত। স্মার্টফোন কিনতে গেলে কি করি? প্রথমে দেখি যে কতগুলো কোম্পানির স্মার্টফোন আছে, তারপরে দেখি কি যে এই প্রত্যেকটা স্মার্টফোনের কি কি ফিচার আছে, তাই না? তারপরে আমরা ডিসিশন নেই যে আমাদের পকেটে কেমন পয়সা আছে, আমি এইটা কিনবো কি সেইটা কিনবো, এই জিনিস। এই যে কতগুলো কোম্পানি আছে এদেরকে বলা হয় অল্টারনেটিভস, আর কতগুলো ফিচার আছে এদেরকে বলা হয় ক্রাইটেরিয়া। ঠিক আছে? তো এইটা যেমন আমরা মুখে মুখে ভাবনা চিন্তা করে নিজে নিজে প্ল্যান করে স্মার্টফোন কিনি, সেই জিনিসটাকে আমি ম্যাথমেটিক্সে একটু অন্য সেন্সে নিয়ে যেতে চাইছি। মিনস আমি পুরো কনসেপ্টটাকে ম্যাথমেটিক্যাল ওয়েতে ব্যাখ্যা করতে চাইছি। কারণটা হচ্ছে যে ম্যাথমেটিক্স ফর অল ইজ অ্যান্ড এভরিওয়্যার উই ক্যান অ্যাপ্লাই দ্য ম্যাথমেটিক্স অ্যান্ড গেট এ ফ্রুটফুল ডিসিশন for buying some products, maybe smartphone, maybe bike, maybe scooter, maybe four-wheeler or anything else. Okay, so to do this, we are using this probability little bit, and then Bayesian theory, all of you know, those are sitting here, I think physics, chemistry, mathematics, you know little bit in HS, probability you have studied. That probability concept I have introduced here. Another thing is there, if you look the slides, there are two words, three way. Bengali it is called তিনটে দিক। তিনটে দিক কি কি আছে? আমরা কোনো কিছু জিনিস কেনার আগে ভাবি ইয়েস কিনবো, না অনেক সময় কি করি মধ্যবর্তী পর্যায়ে থাকি, হেজিটেন্ট। সেই জিনিসটাকে আমি ম্যাথমেটিক্সে নিয়ে এসেছি। ওকে, সো লেট আস টু স্পিচ অ্যাবাউট দিস থিং ইন ম্যাথমেটিক্স। If you look here, the title is a three-way framework for multi-attribute decision making. Three-way means there are three. One is yes, another is no, another is the middle part. That is the thing, three-way framework. Okay? And then multi-attribute decision making means that we have some alternative, we have some criteria. By the way of mathematical approach, we can select which criteria, basis on the criteria, which alternative will provide a best decision for me to buy a product or to make a decision. Okay? So this is my overview of the talk, where decision making means everything we are making some decision. Whether we organize the conference or not, we can make the decision. That is the called decision making. Or if you look in a chair, some person is there, there are only 2 seats. More than 10 people are coming for interview. Then those are sitting in chair, they can select only 2. So this is the way of decision making, how we can select. So this is the decision making and MADM, three-way decision making, as well as why 3 also there. Control L. তাহলে ফার্স্টে লিঙ্কে যেতে হবে। Now it's okay. Enter screen, enter screen. দেখি দেখি এটা ক্যান্সেল করতে হবে, এটা ক্যান্সেল করতে হবে, এটা পুরো ক্যান্সেল আছে তো? আচ্ছা, ম্যাটারটা কোথায় রাখা আছে?
এখানে আছে স্যার, এই ডিতে আছে।
ডিতে আছে তো?
ঠিক আছে, কন্ট্রোলে
কন্ট্রোলে ঠিক আছে, হয়ে যাবে। এই পিডিএফ এ কন্ট্রোলে কি আছে রে? ফুল স্ক্রিন এবার চেক করে দিন। ঠিক আছে, হাইড করে দিন। So now it is visible to all of you? Yeah, now it is visible to all of you. Fine. So then we have considered here some of the discussion about the loss function, relative loss function, expected loss function, and then make the decision rule. And thereafter we can get some outcome and significance, and thereafter what we can do for the next generation, means the future scope. Okay? First, oh, slow. Wait. First, you see what is decision making. Basically, a decision making is a commitment to a single course of action. What I told you at the beginning, if we have a single post, but 10 people are coming, we want to take only 1 people among 10. That means the decision making is a commitment to a single course of action. In the year 1993, Klendorfer et al., means his research group, decision making is the intentional and relative choice in response to perceived needs. Now I come to the alternatives. Alternatives, as I told you at the beginning, how many alternatives you have, means an alternative is a potential course of action. And what is an attribute? Attribute and criteria more or less same. Attribute means an attribute is a quality of an alternative that is related to its desirability. What we need, that means the feature of some kinds of what you want to purchasing. Quickly sit for it. Okay. Now I can say here multi-attribute decision making. It has become more and more difficult to see the world around us in a unidimensional way and to use only a single criterion when judging what we see. The meaning is like this: nowadays it is not enough to handling only single kind of decisions. We are always looking for the multi-criteria decision makings. That means multi-attribute decision making. At a time, we are considering more and more attributes to handling the decision making process. In another way, what is an MADM? MADM is a process of evaluating real world situations. Means we are considering the problems from the real life problems, based on various qualitative, quantitative attributes in certain, uncertain, risky environments to suggest an optimal course of action among the available options. So this is actual MADM problem. Next. Now if you see these kinds of attributes and alternatives, as at the beginning I told you, we want to deal these types of problems by the way of mathematics. The simple concept is we have to design these alternatives and criteria in a matrix. So matrix is like this here. If you look here, the horizontal, we are placing all the criteria, meaning by C1, C2, Cn. Criteria and alternative all are same. And alternatives, A1, A2, Am, we are placing in vertical. So the corresponding matrix, if you see, so this part x11, x12, x1n, and x21, x22, x2n, and xm1, xm2, xmn, this is actual the evaluation value with respect to the alternative AI with the criteria or attribute Cj. So this is our decision making matrix. We will do everything by choosing this decision making matrix. Those are sitting here, physics, chemistry, you know, all of you the matrix. Mathematics people already know what is matrix. So at the beginning, what alternatives and what attributes we have, we are representing these alternatives and attributes in a matrix. Now we want to do by using this matrix in the varieties of operations. As well as if you see here the weight vectors, means W1, W2, Wn's, we are giving the priority which feature or which attributes we have to give more and more preference. That is putting by the weight. Okay? Next. So, two examples I am giving here in a simple way. One is, a consumer while buying a car will pay attention to a series of attributes of a car, such as price, safety, capacity, size, status, fuel consumption, and so many things. In a similar way, manufacturers wants to select supplier on the basis of sustainable attributes such as cost, quality, eco-friendliness, responsiveness, etc. So these are the simple examples of MADM. Now you see these kinds of diagram we can consider for handling MADM problems. What is there? At the beginning, just at the bottom of this thing, alternatives are there. Alternatives we are placing here A1, A2, Am. And then, next hierarchy, we are placing the criteria or attributes. C11, C12, Cn prime P and Cn prime Q. And again we can go to the categories of the attributes C1 and Cn prime. Meaning is like this. By looking this hierarchy, we have to select only one alternatives. That is the overall objective is that selecting the best alternatives AI. Among these A1 to Am, by looking the criteria and attributes, we can select the corresponding alternative AI. Next. Now see three-way decision making. This has a nice example on today's scenario. All of you, those are already more than across this 18 years. They are cast their vote. At the beginning, you can select to press the button to a candidate or to select another candidate. Nowadays, there are one more option is there. That is called the nota. That means the three options automatically coming here. One, you can select the candidate, or you deselect the candidate, or you have an option, you cannot cast your vote also. That means the three decisions in your hand. That is representing here the mathematically. How? We interpret three-way decision. I am using the short abbreviation TWD, is a trichotomous thinking, which introduce a third option to dichotomous thinking with two options. With this TWD, what we want to do? We want to move from true false to true unsure false. If you look here, three decisions are coming. In a similar way, black and white. Okay? In between, there is a gray concept is also there. So, black, gray, white. The third, yes or no. I can select here yes, maybe, no. So, these kinds of activities we can represent by mathematically. It is say three-way decision making, a third. And then what we can do here? We can do by making the three decision in a trisection. How? We interpret TWD in terms of the notions of parts and whole as given in a trisecting and acting T&A framework of TWD. The basic idea are to divide a whole into three parts. Next, to devise the most effective strategies to act upon the three parts. As we are moving from 2 to 3, so what region we have, we can divide in three parts. And then we can making the strategy to select any one of them among these three. Triad. We interpret TWD with reference to a common practice of using a triad or triplet consisting of three elements or three components. A triad offers sufficient complexity in terms of individuals and relationship between them, and at the same time is simple enough for memorizing and processing. So this is the three way. We can divide in a different region in a three parts. Now we will apply some decision making process from this three region, how you can select a particular option. This is called, the total component is called three-way decision making. Next. Question is coming here, what is the necessity of this three-way decision making? Actually here, handling uncertainty and ambiguity. If you collect the data from real life scenarios, then data is not in a exact form, precise form. Means I can give a simple example to you. In a market, fish market, those are selling the fish. They don't know how much demand will be available for the customers on today's market. They can choose a fictitious amount and then they can sell the fish. That means here, this amount is not precise. They guess that maybe 30 kgs fishes will be sold on today. But notice that on that day, more demanding may be arise or less demanding may be arise. That means in a real life problems, if you collect the data, data is not in a precise form, not the real numbers. So the numbers will be imprecise form. You will not get the data. Okay? That means first you see handling uncertainty and ambiguity. TWD model acts on intermediate option as for example defer and undecided, allowing decision maker to delay committing to a choice until further information is gathered or ambiguity is resolved. Second one, improve decision accuracy. Means what decision we want to take, by mathematically if you consider the decision should be accurate, then you have to consider this three-way decision making problem. Meaning that by introducing a third category, decision maker can avoid prematurely rejecting or accepting alternatives, especially when the evidence is borderline or insufficient. Reflecting realistic decision scenarios. Means if you consider the data from real life scenarios, then three-way decision making is a very attractive as well as powerful tool to get a fruitful decision. That is the reflecting realistic decision scenarios. Enabling decision models, TWDM integrates necessarily with advanced decision framework like fuzzy logic. All are using the bike. If you look in a bike, somewhere written DeFi logic, means the anti-braking system. Means in fuzzy set theory, basically in the year 1965, the intelligent person, Jade, who invented this concept. Thereafter, many more research is going on, And nowadays, in a car, luxury car or in a bike, they are using the fuzzy logic concept. Basically, this fuzzy, this word is come from in the year 1965, developed the concept set to the advanced part. This is called the fuzzy set. Okay? So, this fuzzy logic and rough set is also another Z. Pollock who introduced this concept in the year 1982. Just all of you know, those are sitting here, the mathematics people, they know equivalence class. I am using later on. This equivalence class is coming from the abstract algebra. Okay? That means by using this equivalence class in rough set, this three-way decision making rule is more and more finite. And probabilistic models nowadays, probability and statistics you have studied in 10+2 level in HS. Okay? And later, the advanced version of probability in BSc level is also there. And in MSc, there are also the advanced version of probability statistics is there. This is called the stochastic process. Nowadays, you know, machine learning, data science, AI, all are the advanced version of probability. Means if you have a good idea about on the probability, then there is no problem at all to implement the machine learning and data science as well as the AI also. AI means artificial intelligence. All of you know that people are saying that after getting launching this AI, many people lost their job. The main way is in AI there is a huge program, a big program is there in Python. Once you type the word in Google search engine, then everything will come automatically fraction of seconds. That is why the people are losing their job. So these kinds of AI and machine learning as well as the data science basically come from mathematics. We are not in a position to apply this applied versions of this mathematics for getting this such kinds of AI and ML and data science also. But those are interested to make the combined with this mathematics to the real life scenarios, they are automatically getting these kinds of informations for AI as well as data science as well as the machine learning also. Support for iterative processes. Iterative process, you know, for numerical analysis, whenever you extracting some roots, we are basically using the iterating process. And after that, we are making the convergence of this thing. And then finally, we come to here the risk management. Risk is everywhere. Okay, you are coming to college here by traveling a bus, by riding a bus. There is also risk. So risk is always, everywhere is there. So how you can manage the risk, how you can reduce your risk, life risk, that is also managed by this TWD, means risk management. Next. So this is the decision theoretic rough sets. As I told you, in the year 1982, Z. Pollock introduced the concept of rough set. Just simply, actually, those are using here this online access, there will be echo. Okay. So I request to you, please go to the outside and use this internet, this online version. Actually, here if you look this part, U is a finite and non-empty set. And U, we are defining here capital E is an equivalence relation. You know equivalence relation, what is this? Means it is reflexive, symmetric and transitive. Okay? In a particular relations, if you define and three properties are valid, well and good, then you can say it is equivalence relation. Here this equivalence relation I am using E. And capital U is the finite and non-empty set. And thereafter we use this pair as an approximation, U, comma, E. And then we apply here the equivalence class. Equivalence class is nothing but a set. Okay? You see that equivalence class we are denoting here by third bracket. And this is the collection of that equivalence class. How? Collection of elements from the universal set U. We are denoting here that X will be Y such that XEY. What is XEY? XEY is the equivalence relation. We collect that element from the non-empty set U which will satisfy XEY. That means X is a simple set. And if you look here the corresponding figure, there are two options. One is the lower approximations. We are using the lower sign, APR. And upper approximation, we are using the upper bar. And this is the portions I want to look here. this is the blackish portion square size. This is the approximate, where everything is there, real. And then, if we consider the oval shape like this is actual shape, and this is lower approximation, and this part will be the called upper approximations. And the whole portions, you can say granules of knowledge. Whenever you make a decisions, then decision is not fixed. It is somewhere fixed, just you can pick it, not like this. It can be spread, some of the portions, some of the boundaries. That is called the granules of knowledge. And whole things I am denoting here the set of objects. Now if you look here, the lower approximation, what is there? X belongs to U such that the equivalence class is a subset of A. What is A? A is a non-empty set, of course. I have mentioned here the subset A is a subset of U. That means it is non-empty set. And this one upper approximations, this will be collection of X belongs to U such that this equivalence class meet A not equals to phi. If these two relations are satisfied, then you can say one is the lower approximation, another is the upper approximation. What is the lower approximations? This part is called lower approximation. Means if this is our set of objects, then this is the common. Means automatically we can get everything. But for the upper approximation, if you see, some of the portions is extended like this. So this is called upper approximation by using this mathematical symbol. Next. Now these two lower approximations and upper approximations, we are denoting some of the words here. One is the possible region or positive region, POS of A. Why it is positive region? Because if you consider set of objects and inside this the lower approximation is there. So positive region is a small portions where everything is there. And negative region, we can consider the non-empty set minus positive region meet boundary region. What is this boundary region? Boundary region, if you make the subtraction between this lower and upper approximation, something will be there. If nothing is there, then the decision cannot be made. So, this boundary region should have some element. As all are the set, so this will be not a phi. And now with the help of this alpha and beta, what is alpha and beta? Whenever you take a decision, some value is required, unless otherwise you cannot take the decision. So that values means a threshold value can be put here, alpha and beta. And this alpha and beta we can define in three regions. One is the possible region. How we can select this possible region? Probability of A with this greater than equal to alpha. If this region is valid, this inequality is valid, then you can say it is the possible region. And next, if the negative region, if you consider this element, then this probability less than equal to beta. And if alpha and beta lies within this probability of A by equivalence class, then the corresponding region, you can say the boundary region. And this probability of A by equivalence class is called the conditional probability. You know the conditional probability because in HS syllabus, conditional probability is there. Probability of A by B, nothing else. So, probability of A by B, we are calculating like this symbol. What is this symbol? Equivalence class meet A with another mod sign is there. This is not mod sign. This is the cardinality. Cardinality means in a set, how many elements are there? If you have a set contain 4 elements, then you can say the cardinality of that set is 4. In a similar way, the equivalence class, what we have defined at the beginning, that will be we make the cardinality also. So this cardinality of these two ratio will provide the corresponding conditional probability. Next. Now, one of the scientists, Chinese scientist, he proposed this three-way decision theory. with the help of rough set theory and Bayesian theory. Bayesian theory is the advanced version of probability theory. Actually, I am not going to much more about the Bayesian concept. Just we are applying the Bayesian concept and then I'll introduce the concept of TW theory. What is there? Actually, in three-way decision making, what we want to do? There are two states. One is A, another is negation of A. Negation of A means if we consider a complement of a set, then the complement part will be called the negation of a set. Sure? So here the same concept, two states, one is in A, another is not in A. We are using the not in A sets by this symbol, and three actions. As I told you at the beginning, if you divide the three parts, fine, and then some strategy should be there in three actions, three parts, and thereafter we have to pick one of them. How? By using the mathematics, we are calculating the conditional probability, and then we fix the threshold value. Means if the probability value is more than alpha, then we can move this part. If it is less than beta, then we can this part. And if it is lying between this and this, then we can move the boundary part. So these three regions can be calculated by the way of these three decisions. So three actions here I am choosing. One is AP, another is AB, another is AN. In which the three actions denote by X belongs to positive region A, X belongs to boundary region A, and X belongs to negative region. That means the three actions, one is AP, another is AB, another is AN. These three actions we are considering like this, and then we can decide which region we have to select, we have to pick. Next. Now you see, what is there? As already you have divided the two states, one is A, another is a negation of A. That part here, these three actions I have automatically put here vertically, AP, AB and AN. This is lambda PP, and lambda NP. In a similar way, negation of A, lambda PN, lambda BN and lambda NN. Now, we see here by considering the loss function. How? We can measure this fact by applying the loss function. If it is more loss, then we can reject the decisions. If we consider that small loss is there, then we can pick this side. And these loss functions we are denoting here the losses of actions AP, AB and AN for state A respectively, when the objects belongs to A. And similarly, lambda PN, lambda BN and lambda NN denote the losses incurred for taking actions AP, AB, AN respectively when the objects belongs to A. One thing I want to mention here, if you know the three-way decision making rule, then nowadays the people are investing their money in mutual fund, in the stock market also. And that stock market, these kinds of rules are frequently using. Of course, with the help of mathematics, nothing else. Means if you know the mathematics very well, then your future will be bright if you apply the concept of mathematics in different and realistic scenarios. And if you look here, the loss functions, lambda PP, lambda BP and lambda NN, this is the corresponding activities, means the relation of this loss function like this, and lambda NN, lambda BN and lambda PN, also another inequality for the loss functions when the state belongs to A and the negation of A. Next. Now question is coming here, we have a loss function. How, if you have only one state is there, A and negation of A. If we consider more and more states, then we have to calculate more and more loss functions. That means we have to generalize the concept. How? For X belongs to A, we denote here the relative loss functions R of, R means the corresponding loss functions we can consider here. AI divided equivalence class of A. Actually, this is not a divided symbol. Actually, what kinds of conditional probability we are measuring, the same thing here also, is called the expected loss when taking the action AI is equal to PBN. PBN means one P means positive region, B means boundary and N means negative region. And it can be calculated just a simple combination of these two things. you look here, this loss function, expected loss, R of AP by equivalence class will be how much? Lambda PP, what we have defined in this table, then probability of A by equivalence class plus lambda Pn, probability of negation of A by equivalence class X. In a similar way, we can calculate R of AV and R of N. It is very careful that, you know, a particular event, the probability of A and the probability of negative of A, how much? Value is 1. Here also the same thing. Probability of A by conditional X and probability of A by negation of expected equivalence class will be cannot be exceed 1. It should be equal to 1. Okay? Next. Now, from this expected loss, we can make a decision. Our main aim is to take the decision. So decision rule is there. How? Decision rule can be taken like this. If we see that the expected loss R of AP equivalence class less than R of AB equivalence class and R means loss function, R of AP divided equivalence class this, then we can decide that X belongs to possible of A. In a similar way, if these kinds of inequalities are valid, then the corresponding X belongs to boundary region A. If these kinds of relations are valid, then you can decide X belongs to NA. The question is coming here, already you have divided into 3 parts. Which part we have to select? For selecting the particular region from this triad, we have to make a rule. The rule is like this, by making the probability calculation of this probability. And after calculating the probability, if you look that this kinds of scenario is happened, then the corresponding decision we can decide what we want to make the decision, it is goes to the possible positive region of A. In a similar way, if this kinds of relation is valid, then you can decide X belongs to boundary region. Means this is our nota. That means yes, no, like this, maybe. And this one is X belongs to negative region if these kinds of loss functions are validating the corresponding inequality. Next. Now, as you remember that alpha and beta, we have decided earlier for the threshold value for the expected loss functions. Now we want to introduce another one also, gamma, by like this. Means there are so many types of decision rules we can adopt for taking a final decisions of our decision making process. Okay? So if you look here, this is P prime, B prime, N prime. Earlier it was P, B, N. Now it is P prime, B prime, N prime. Means we are making the decision more and more finite. If you say that probability of A by equivalence class greater than equal to alpha and probability of A by equivalence class greater than equal to gamma, and alpha, beta, gamma, these are the threshold value provided by the decision makers. Question is coming here, how the decision maker will provide? Decision maker means in an interview board, sometimes those are sitting in the interview board, they can fix for experience 10 marks is there. For academic qualification, some marks are there. And for the exam, some marks are there. So these are the actual here alpha, beta, gamma. So based on this alpha, beta, gamma, if you calculate the corresponding probability, then we can make the decision by whether the candidate will get the job or not by making the positive region X belongs to A. If it is not, then X belongs to boundary region, X belongs to negative region. That means the mathematics, if you use in a particular way, by realistic sense, then everything is possible with the help of this mathematics. And this alpha, beta, gamma threshold value can be calculated also with the help of these loss functions, what we have defined at the beginning, A state and negation of A state. You see here alpha equal to like this, beta equal to like this, gamma equal to like this. Okay? Okay, next. Now this is the another rule for getting the finite decisions. You see here I am noting P double prime, B double prime and N double prime in that way. Now next move. In that way, to get a finer and finer decisions, I can decide that I can make the decision rule by more and more finer of this part. You see, this is the decision matrix, nothing but the previous one. Just we make the subtraction, this is 0, means this one will be how much? Lambda BP minus lambda PP. So this makes the subtraction 0 for making the calculation so easier. That means we have to always move how we can make the less calculation and get the finite decision. So this is this thing, my relative loss functions, we are using the another term. In front of this loss function, we are using here the relative loss function for getting more and more finite decisions. Okay? Next. And again, the threshold value alpha, beta, gamma, what we have defined earlier, the same thing here also calculated by alpha prime, beta prime and gamma prime also. So no change at all. To make the finer and finer decision, the less calculations, we are using different type of mathematics for getting this alpha prime, beta prime and gamma prime. Next. Now we are coming a simple example here. Let us suppose there are loss function of TWDM problem as shown below. AP, AB, AN, we are using here A and negation of A. A means 1 to 5. Corresponding loss function we are defining like this. Negation of A we are defining 7, 4, 2. Now what rules we have implemented earlier, using 1 to 3 we can easily calculate the corresponding threshold value alpha equal to 0.75 and beta equal to 0.4 and gamma equal to 0.56. These three threshold value we have calculated in earlier mathematical rule what we have adopted. And now if you consider for making the calculation so easy, making this one is 0, how? Means if you subtract 1 from each of the component, then how much? 5 minus 1 is 4, 2 minus 1 is 1 and 1 minus 1 is 0. In a similar way, here the least component 2, so 7 minus 2 is 5 and 4 minus 2 is 2 and 2 minus 2 is 0. So if you calculate the threshold value, you will get the same one, alpha, beta, gamma, what we have obtained for the earlier case. That means to make the calculation so easy and finite, then we are using these kinds of loss functions in that way. Next. Now there are some of the disadvantages of this classical TWDM is there. I am not going to this disadvantage part. We can skip this part. Okay. Now see, actually this is our TWDM, three-way decision making. And another is the MADM, multi-attribute decision making, what I told you at the beginning. How we can make it? Combine these two parts. One is consider the MADM problem described earlier in which Xi is the evaluation value, means the corresponding matrix what we have designed, and of the corresponding state AI with respect to alternative, with respect to this alternative AJ and with respect to the attribute CJ. And Xij belongs to an interval, means mean value and max value be the evaluation value. And the state we are choosing here, one is CJ, another is negation of CJ. Two states I am choosing here. And here AI belongs to CJ indicates that AI possesses the property CJ, and AI belongs to negation of CJ indicate that AI does not possess the property CJ. Three actions we have chosen here, AP, AB and AN. Okay, indicate the decision of acceptance, non-commitment and rejection respectively. Okay, so these are the integration between TWD and MADM problems. Next. And these are the same things for by this mean value and max value. And if you calculate this part, this AP, AB, AN by this one 0 and this is sigma is the corresponding another threshold value, for the decision maker can choose it and put it here also, and then we are making a relationship between this the loss function with this evaluation value. Next. And this is a simple example here. Decision maker evaluate two objects A1 and A2 according to their performance in criterion CJ, and Xij belongs to 0, 1. Xij means 0 to 1 means mean value and 1 is the maximum value. And X1I, X1J 0.7, X2J 0.4 and sigma is the threshold value decided at the beginning 0.3. The relative loss function A1, A2 can be calculated like this by the previous table what we want to show. And if you look here, this A1, A2 belongs to CJ, the losses of putting A1 into the boundary region and the negative region 0.21 and 0.7 are larger than the loss of putting A2 into AB and AN 0.12 and 0.4. The reason is like this, the evaluation value satisfying this to this 0.7 greater than 0.4, which means that the performance of A1 regarding CJ is better than A2. So by this inequality, we can decide, we can consider the performance of A1 regarding CJ is better than A2. So taking the action of rejection or non-commitment A1 suffer a higher loss of A2. Similar facts happen for other case also. Next. Now, instead of only two states, A and negation of A, I can consider more and more states. Then what we want to do? We just make the summation, nothing else. And that summation part we are doing here. And this is the reflection of aggregated loss functions by making the summations for all states by corresponding the loss functions for action AP, AB and AN. Next. And this is the another threshold value alpha I and beta I. Means if you have a more and more criteria, more features, then we can make the summations what mathematics we have did earlier. We just make it the summation part, and that summation will reflect here the corresponding threshold value alpha I and beta I. Next. So this is the conditional probability what I told you earlier. There are so many advanced techniques are available here. You can apply this technique, you can get more and more finer result. Next. And this is another rule also there. Means earlier we have adopted P double prime, B double prime, N double prime. Now we are considering P triple prime, P double prime and N triple prime. Okay? And if you see this is the corresponding probability greater than equal to alpha I, then we can decide our criteria belongs to the alternative belongs to the positive region C. And another one boundary region, another one is the negative region. Next. And these are the algorithm of steps, how we can take the decisions or how we can collect all the alternatives and criteria and defining here step by step to get a 3-way decision rules. Next. So there is a problem. If you look here, more criteria are there and more alternatives are also there. That means here are 5 alternatives and 5 criteria are there. So with this alternative and criteria, we can make a larger table. Next table. Next. You see, this is the corresponding table. And from this table, we can make a finer and finer decisions, alpha I, beta I, and gamma I also, and to take a 3-way decision rule, which activities and which criteria we can adopt for the alternatives. Next. And this is the corresponding calculations for this problem. Next. And finally, we are calculating here the values of alpha I and beta I corresponding the alternatives, means A1, A2, A3, A4. Next. And with this probability of this thing, and if you look here, the final decision positive decision of C, there are A1, A2, A4. Means we have 5 alternatives. Among these 5 alternatives, we can select here the possible positive region of this criteria A1, A2, A3, and the boundary region nothing is there, and in negative region there will be A3 and A4. So with this help of probability and the Bayesian's theory as well as the TWD, 3-way decision making rule, we can decide if you have a more and more number of alternatives as well as the criteria, then we can decide by mathematically which criteria you can select and which alternatives you can pick up for your problems. Next. So this is the conclusions. We have to conclude here because another 12:15. কখন আছে? 12:30. Okay. Means in a conclusion part, if you look here, what we did here, actually handling uncertainty, at the beginning I told you, each and everywhere, if you collect the data from the real life scenarios, the data is not in precise. Precise means not in an accurate form. It has some spreads, left spreads as well as the right spreads. So, handling uncertainty, if data is there, then if you adopt the rule of 3-way decision making, it will be finer and finer to make a decision. Dynamic adaptation, it aligns well real world decision process where immediate decisions are not always optimals. Sometimes you look, some persons are sitting in an interview board. They can take a decisions, but some candidates giving the interview, thereafter some hesitancy is there. They can stop their decisions. And later, by opening this file, they can take the decision. So, if you adopt the three-way decision-making rule, then in such scenario, this rules is very much important. That is here, it aligns well with real-world decision process where immediate decisions are not always optimal. Decision makers can prioritize options for acceptance or rejection while deferring borderline cases for future evaluation. Applicable in multiple contexts. I have already discussed here in so many scenarios, especially if you consider here in healthcare or business or artificial intelligence, where decision making often involves complex trade-off and incomplete data. Sometimes in the healthcare systems, a patient comes to the doctor and immediately decide that whether operation is required or not. That means the operation process is pending. In such scenario, if you apply the three-way decision-making rule, it will be enough, okay, to get the situations whether the patient is required for surgery or not. So this kind of adoption rule is very important here for the three-way decision-making rule. Integration with MATM technique, three-way decision-making can be seamlessly integrated with MATM methods such as TOPSIS. There are so many advanced methods as there are TOPSIS, AHP, Prometheus to enhance decision precision, especially in case involving fuzzy and probabilistic informations. And limitation of this method is also there. While effective, the model may increase the complexity of decision-making framework. Future research could focus on optimizing deferment thresholds and developing computational looks and computational tools and exploring application in high-stakes decision environments. Means some of the situations in this method, there are some drawbacks also there. So those are sitting here, if you interest to do some future work, then you can remove that drawbacks by implementing the computational tools in other way, maybe applying the AI or machine learning or data science, something like this. Next. So these are the references. Actually, wait just a minute. If you look the reference number 6 and 7, actually myself and my scholar as well as some foreign collaborators, we are developing this paper and publish this paper in a very good journal, SCI journal. Expert system with applications, those are here in operation research, they can automatically look the quality of this journal is too much high. And apply subcomputing also, this impact factor is 8 point something. This one is also 8 point something in the year 2024. Next. And another is also, this is artificial intelligence review. This is a very good journal whose impact factor is 12 point something. And others part we have also incorporated here. Some of the fundamental work I have noted here, this PALOC as well as the AU work and the Zelani work also. Next. Next. So, thank you very much for your patience with these 45 minutes lectures. One thing also I mentioned here, some parts of my lecture, I realized that it is beyond your head, means it's going to the tangent direction. I realize this fact, but I want to give a small message to you. If you love mathematics, then you can take the decision, a decision-making tool in a very fruitful way. That means mathematics, all of you know that it is a queen of science. It is sure, but you have to apply this queen of science in a multidisciplinary subjects. If you apply this concept, then you can take a fruitful decisions by applying the concept of mathematics. So you love mathematics. If you love mathematics, mathematics will also love you. With this message, I end my lecture here. Thank you very much for your kind attention.
Yes. At first, thank you so much, sir, for your enlightening and thought-provoking keynote lectures. If there are any questions from audience, they can ask. If there are any questions from audience, they can ask freely. Sir, there is a questions from audience.
Sir, I have one question at the slide number 19. There are alpha, beta, gamma and alpha dash, beta dash, gamma dash. Okay. So, is this quantity are dimensionless? I mean, is there any dimension?
I get your question. Actually, we are calculating here this loss function here, na? Alpha prime equal to. Go back to the previous slide. Okay. Again, back. Again. Just a minute. No. Back. Next. Yes, this one. This is the loss function. Okay. This AP, AB and AN. Okay, and later if you see, just for this example, we are putting a scale 1 to 9. Okay. So of course it is dimensionless.
Okay.
We are putting a scale 1 to 9 because we have a criteria, means features.
Yes,
Maybe
sir.
the price, maybe the index.
Yes, sir.
If you consider the price, it is in rupees.
My question is, sir, price is
Price
dimensionless?
is no
or
price
some,
in rupees.
Some features.
Price in
is
rupees.
Okay.
In other features, if you consider, it may be the another units.
Yes.
That is why we are considering here the scale 1 to 9.
Okay, sir.
That is why all are the dimensionless. Yes.
Okay. Another is, when we are calculating alpha, beta, gamma, alpha
Yes.
dash, beta, gamma, is there any mathematical coding or it is based on some algebraic
This is a very good
equation?
question. Actually, if you have only one state, then you can consider a state and negation of state.
Okay.
But whenever you consider 6 or 7 or 10 or 15 states, then 15 and there will be negation of 15.
Okay.
So 30
Okay.
components will be there. So in such scenario, you must write a program.
Okay, sir.
Unless otherwise, the computational part will be very difficult.
Got it. Thank you, sir.
Okay.
Any more questions from online platform participants? No question. So thank you so much, sir. Once again, the topic is now hot cake in market, AI, ML. There is a very much important topic. This is. Any students from other disciplines may learn these things also because for their better future, I think. Thank you. Here we finish our keynote session. Then we will go to the next session after 5 minutes. Thank you, sir. Thank you.
Hello. Welcome to our conference, sir.
Hello, do you hear
Hello,
me?
sir.
Perfect.
Welcome. Sir, please wait for 2 minutes. Sir, we are
Okay,
organizing. Okay, sir. So time is
perfect.
12:24 now. So we will just start at 12:30.
Okay.
Dipanjana, you can start. Dipanjana, please.
Sir, welcome all of you again. There will be a lecture from Professor Milan Ladik sir. Sir is an eminent professor of Charles University, Faculty of Mathematics and Applied Physics. He is the head of the Optimization Division and Interval Methods Group. His research area is interval analysis and optimization and operation research. He has more than 150 research articles in popular journals. He has written two books. One of is an linear algebra and another is the interval linear program. Sir, we disassemble now for the invited lecture Professor Dr. Milan sir. He will be speaking on an invitation to absolute value equations from theory to computation. Over to you, sir. Very welcome from us.
Thank you very much. So I will share the slides right now. So,
Good afternoon, Professor Milan. I am Shankar.
do you see the slides?
Yeah. Slide is visible. No issue. Make it larger.
Perfect.
Make it larger.
Okay. Is it okay now?
Yeah. Is it possible to make it
So
larger?
thank you very. Maybe I will make some notes in the slides, but I can do it like this. Is it better?
ওইখানে ওইটাতে make it the full screen. Okay, by noting this you see that yes.
No.
Yes. Now it is okay, fine.
Is it fine?
Yes. It's fine.
Okay. Can I start?
Yes.
So, thank you very much for the invitation. It's only pity that I cannot be present at your conference, so I have to join online in this form. And thank the organizers for inviting me. It's very wonderful for me. So, what I will speak about about absolute value equation, which is quite a recent topic. Let's say the last 15 years, and it went a great development in the last years. So I will just like to share some of the results. It will be just a brief overview from the theory.
Hello, Professor.
Some methods.
Sorry, just you can increase your volume. Is it possible to increase your volume?
I am not sure how to do it right now. Let me check. Is it better? Is it better now?
Now it is little bit more.
Can you hear me?
Chup.
Just a minute.
Yes, now it is okay, fine.
Perfect. Can you hear me?
Yes, it is fine. Continue, please.
Perfect. Thank you. So
Yes.
let's go. So what's the problem? Definition. So the problem is like the following. Everybody knows the system of standard linear equations, which is like ax is equal to b, and this is well known from the beginning of the school. Everybody knows about it. So we will make just a small change in the definition of the system, and we will involve one small term, the absolute value of x, which is meant component wisely. So every components of the vector x are in the absolute value. And this is a very small change in the problem, but it changes a lot the problem itself, because from an easy problem of linear equations, it becomes a very difficult problem of absolute value equations. So from now on, we will focus just on this quite simply defined but hard to solve problem, AVE, absolute value equations. Of course, there are different variants of this problem. We can extend it and generalize, but we will just focus on this particular basic canonical problem. And for our convenience, it will be always on the top right, just that you can see what's the problem we are speaking about. So the solution set is defined in a standard way. It's the set of all x such that they satisfy algebraically the AVE system. And how it looks like geometrically. So it can be a finite set or an infinite set. In case it is finite, it can have 1, 2, up to 2 to the power of n points. This is the very simple case where we have the maximum 2 to n isolated points, because every sign vector plus minus 1 vector satisfies this equation. And indeed, every number between 1 and 2 to n can be attained as a number of solutions of a certain AVE system. How it looks like more in detail. So in general, it is a non-convex, disconnected set, but fortunately, in each orthant, it forms a nice structure. It has a structure of a convex polyhedron. This is quite easy to see because an orthant is described by a sign vector S, and in the orthant we can easily get rid of the absolute value because we can replace the absolute value just by taking the sign multiplied by the variables. In this case, we get rid of the absolute value and we have a standard system of linear equations, which means that in every orthant determined by a sign vector, it forms a piece of this affine subspace. To have some view how it can particularly look like, so let's consider several examples in 2D. So 2 by 2 examples. So here you can see in blue the solution set, which consists of one segment and one semiline. In this case, you can see it is, of course, non-convex, but still it is connected. But in the second example, it is disconnected because the solution set consists of one isolated point in the negative orthant and one semiline in the positive orthant. So you can see that the solution set has quite complicated structure, and this makes the problem difficult. Originally, the motivation for solving this system of equations was due to its quite strong connections to LCP problem, the standard linear complementarity problem. Just recall how it is defined. The standard linear complementarity problem is also an algebraic system of equations in which we have non-negativity of variables. We have a linear dependence between variables, which is easy to solve, but the problematic part is this complementarity, which means that every variable is, for each I, either the ith variable yi or zi is 0. And this is quite complicated combinatorial structure. And it is equivalent to AVE, and basically we can easily transform AVE to this LCP and vice versa. And it is quite useful, so I will show you this reduction because we will use one of them in the later in my talk. So just for technical reason, we assume that A plus the identity matrix is non-singular, and then the idea is very simple because we split the variable in the difference of the positive and negative part. The positive and negative part are non-negative vectors, but they satisfy the complementarity. So now you can see that we have the complementarity, and the absolute value can be easily replaced as the sum of the positive part and the negative part. Just substituting for the absolute value, we rewrite the absolute value equation in this standard linear system of equations. And just by rearranging this equation, we have the linear complementarity problem. So this is one side, how to reduce AVE to LCP, and the opposite direction works in a similar fashion. We just, again, for technical reasons, assume that the matrix identity is non-singular. And then the reduction is based on this simple observation that for two numbers, the product of the numbers is 0 and they are non-negative, if and only if they satisfy this equation. And by using this simple idea, we can easily extend this to vectors, and we rewrite the linear complementarity problem in the vector form in this equation. And then we can just rewrite this equation to have the standard form as is written on the top, so that we just multiply by these inverses, and this is just the technicality. So this is the opposite direction. So you can see we can easily rewrite the AVE system to LCP and vice versa. So this was the original motivation to study AVE problems, but of course AVE problems appear in many situations because whenever we have the absolute value, we have some kind of system with absolute values. As I mentioned at the beginning, it is a hard problem and it can be easily proved that it is computationally difficult. More concretely, it is NP complete to check if there is at least one solution. This result is already by Mangasarian almost 20 years ago, and the reduction goes as follows. We reduce it from the well-known problem of set partitioning. Recall that the set partitioning problem is the problem in which we have n numbers in this vector A, and we want to split the numbers into two parts such that one part, the sum of the elements in one part is equal to the sum of the elements in the second part. Or equivalently, in the algebraic way, we can formulate the problem as follows. We just ask if there exists a sign vector such that this equation is satisfied, because the plus ones correspond to one part and the minus ones to the second part. So this NP hard problem that we will use, and we just reformulate this problem as follows, because, okay, x is sign vector. This can be represented just by saying that the absolute value of x is the all one vectors. So basically you can see that we have now the system of equations with absolute values. And if we want to have it in the canonical form, as I presented before, so we just can reformulate it in this way just by introducing two auxiliary variables, xn plus 1, xn plus 2, and we have this system of absolute value equations in the canonical form. So you see that the proof was very, very simple, and it was reduced from the set partitioning problem. So now we know that checking solvability is NP complete, and not only that, many problems related to this AVE system are computationally difficult. So let's now more focus on the solvability. So we want to derive the conditions when the system has a unique solution. This is the most typical case, and the characterization uses interval analysis. So this is a very nice connection between the AVE systems and the interval computation. Just recall what is the interval matrix. Interval matrix, we will use just the matrix of this form, and it's the set of all matrices such that the distance between A and the matrix is at most the identity matrix. So basically it means that all the entries are fixed. Only on the diagonal they can change up or down by at most the value of 1. And by using this matrix, okay, and what does it mean that an interval matrix is regular? It means that every matrix inside is non-singular because it is a set of matrices, so the property should be satisfied for every instance of the matrix. So regularity means that all matrices inside are non-singular. And by using this definition, we can now formulate the condition for unique solvability. So this is a very nice result, and it claims that the AVE system has a unique solution for every right-hand side, if and only if this interval matrix is regular. Notice a very nice relation to the standard system of linear equations, because the standard system of linear equations is has a unique solution for every right-hand side if and only if the matrix is non-singular. And in our case, it is quite similar. We claim that the AVE system has a unique solution for every right-hand side if and only if not only the matrix A, but all these matrices are non-singular. So that is a very nice relation and analogy. Also notice in the previous slides, I showed you the equivalence between the AVE and the standard linear complementarity problem. And in the LCP, the condition on unique solvability means that the matrix is so-called P matrix. It satisfies the P matrix property. And this condition is known to be NP-hard, which means that also checking this regularity is NP-hard. So this is a nice condition, nice characterization, but it is computationally difficult, and we cannot do anything with it because it is NP-hard. But what we can do is to introduce some sufficient conditions. And basically there are two well-known and quite often used sufficient conditions. One of them it says that the spectral radius of the absolute value of the inverse matrix is less than 1. And the second one claims that the minimum singular value is greater than 1. So both of these conditions are quite strong and easy to evaluate because this is just some simple linear algebraic problem. And if we know that at least one of these sufficient conditions is satisfied, so in this case, because it's a sufficient condition, so we know that then the system is uniquely solvable, and even more, we can the unique solution compute efficiently in polynomial time, which is a nice property. But what is an open question here, and there are many open questions, so one of the fundamental open questions here is if we know that the AVE has a unique solution for every right-hand side, it means if this condition is satisfied, so how to find the unique solution? So this is the open problem, and its complexity is open. So we don't know if we can compute the unique solution in polynomial time or not. So this is one of the open problems left for future. Okay, here I mentioned that the IVE is efficiently solvable if one of these conditions is satisfied. So just the idea how the method works, it is quite simple because we just use the definition of the IVE and we construct these Picard iterations just by iterating, computing the right-hand side, and this gives us a new vector, and this iterates for every k. And these simple iterations converge in polynomial time to the true solution because the assumption says that these iterations or the mapping is a contraction, so it converges very fast to the solution, and we can, in polynomial time, determine the orthant in which the unique solution lies, and once we have the orthant, we have also the solution. Okay, so this is the proof more in detail because the minimum singular value when it is positive, greater than 1, so it means equivalently that the spectral norm of the inverse is less than 1, which means that the mapping is a contraction. And when the mapping is a contraction, so in that case, we know that the difference between two images of two vectors is bounded from above by the distance of the vectors multiplied by this norm. And when the norm is less than 1, it means that it is contraction and it goes exponentially fast to the unique solution, which is the fixed point of this mapping. Okay, so one slide about non-negative solvability, because I mentioned that many problems here are in fact computationally hard. So it is also useful and nice to have something which is easy to solve, and this is the case of non-negative solvability. So we have this characterization of non-negative solvability. So we know that the system, the IVE system, has a unique solution, non-negative solution for every non-negative right-hand side, if and only if it has at least one non-negative solution for every right-hand side, and this holds if and only if the third condition, meaning that the inverse of this mapping is matrix is non-negative. So because this is easy to check. So we have that also these two cases are easy to check. So the non-negative solvability is polynomially decidable, so it is the property that is easy to check. So one of the few cases which are easy to check. And this non-negative solvability also closely corresponds to inverse non-negativity of matrices. So very old but nice result from 70s by Cutler says that this integral matrix is inverse non-negative, which means that every instance has a non-negative inverse of the matrix if and only if these two conditions are satisfied. And you can see that this condition is easy to check because just we compute two inverses and check if they are non-negative in every entry. And inverse non-negativity corresponds to our problem in the following way, because if the matrix is inverse non-negative, and we know now that it is easy to check by the Cutler's theorem, so then the IVE system has a unique solution for every non-negative right-hand side, and even more, we can compute the solution easily by Newton method, and it takes at most n iterations, which means that we can compute the solution efficiently because we just solve at most n system of linear equations. So this non-negative solvability is the case which is easy to check. So I mentioned some methods, so let's seek for them more in detail. So what are the general approaches for the method? So there are several let's say classes how to approach to solve the IVE problem, and just remind that that in each orthant the solution set reduces to a standard system of linear equations. So if we know the orthant in which the solution lies, then we are done, because we find the solution by solving this linear system of equations. So the crucial thing is here to find the right orthant. So what are the methods that can be used? So we can use the standard Newton method, but we not the standard, because we have to use the generalized Hessians, because we cannot use the standard Newton because here the mapping is not differentiable due to the absolute value function. So we have to use the generalized Hessians. But this is not a big problem, and Newton methods usually work well, just they reduce to solving some series of linear system of equations. I already mentioned the Picard iterations. It is another direction in which we can proceed to solve the problem. The Picard iterations, the basic form is the following one. We just have these iterations in which we compute the next iteration by solving the right-hand side. So it is again a system of linear equations. And there are also reformulation by using some optimization problems. Of course, they are difficult because the problem is difficult, but they have some nice properties as well. So I will now focus more on the optimization reformulations. So many of them are already by Mankasserian, who studied and was one of the founder of this problem and studying this problem. So we can compute the solution by solving this optimization problem, which is minimization of a concave function. So this is of course a difficult problem in general. So notice that in all the optimization problems that we will mention, the feasible set has this form. Why? So we would like to have this solution set, but we know that it is difficult to solve. So we just use one inequality of this equation, because this inequality gives us, you will see in a while, this gives us a convex polyhedron, because this can be reformulated by standard linear inequalities. So in the feasible set, we have just this inequality, and the objective of the objective function is to force the inequality to be satisfied as equation. And you can see why, because we minimize the sum of differences between the left and the right hand side. So if the optimum value is 0, it means we can achieve here the equations. And if the optimum value is not 0, it is greater than 0, it means that we cannot achieve all the equations here, and the system has no solution. So as I mentioned, the feasible set can be characterized equivalently by this system of linear inequalities just by reformulating the absolute value by taking the plus and minus sign, both of them simultaneously. So the optimization problem now has a nice feasible set as the convex polyhedron. So the only problematic part here is the objective function, which is not convex because it is the opposite, it is concave. And as I mentioned, if the optimum value is 0, it means that the AV is solvable. And if it is positive, so it is unsolvable. So even though the problem is difficult to solve, still we know by theory that if the interval matrix is regular, notice that this means that the solution set has a unique solution. There is a unique solution. So in this case, each local optimum of this optimization problem is a global optimum. So it is sufficient to achieve any local optimum, which is nice because many optimization solvers just converge to local optima. So another optimization reformulation is by Mangasarian and Mayer, and they reformulated the problem by using the bilinear or quadratic programming, but not convex quadratic programming, because again the objective function is not convex. We still have the same feasible set, and again the purpose of the objective function is to achieve equation here in the feasible set. And again we have the same property that if the optimization problem has the optimum value 0, then we obtain the solution of the system AVE, and if the optimum is positive, so then the system is unsolvable. We can also try to approach the problem by using the linear programming. So again, we have the same feasible set, all the same here, and we just take some general, we don't know yet now what's the value, some general objective vector C. And what we can claim is the following result. Under quite strong assumptions, of course, the inverse non-negativity of these two matrices, and if you take any positive vector, C as the objective vector, so then by solving this linear programming problem, we obtain the solution of the absolute value equation, which is nice, of course, but the drawback is that the assumptions are quite strong, which is natural because linear programming is easy to solve, and we cannot have an easy to solve method to solve the problem which is theoretically hard to solve. So we can try another approach to linear programming, and in this form, the objective vector is just the product of some vector C, which we'll specify it later, and the matrix A. And now we can show that again under the assumption that the matrix is regular, which just remind that it means that the AVE system has a unique solution. So in this case, we know that there exists some non-negative vector C, such that we obtain the solution of AVE as the optimum of this linear programming problem. So it is a nice result, but of course not constructive, because we don't know which vector C to choose. We know that from theory that there exists some non-negative vector, but we don't know which one is the optimum one. So we can try heuristically to find something, but this is of course some other problem. This is just the theoretical result. But if we strengthen the assumption and we assume not only that the interval matrix is regular, but something strong, this is a stronger assumption, because it also implies unique solvability of the system, but something more. So in this case, we can take the vector C as the Perron vector of this matrix. This matrix is positive, so it has the Perron eigenvector. Recall that the Perron vector is the eigenvector corresponding to the greatest eigenvalue, and the Perron vector is always positive in this case. So this gives us the appropriate vector C. Okay, so this was just some overview of the methods which can be used. Of course, I can spend much more time by speaking about the methods in more detail. But I want to share with you several more points. One of them is some conditions for unsolvability, because I presented to you some conditions for solvability, and of course, for complementarity, I will also present some conditions for unsolvability. So if you remember the slides that I presented you at the beginning of the presentation, I showed you the reduction from our problem, AVE, to the standard linear complementarity problem. And the reduction went as follows. We just rewrote the AVE as this system of linear complementarity problem. And this LCP has this form. It is a system of linear equations, which is easy. Some non-negativity of variables, it is easy. But the problematic part is this complementarity. So the idea to obtain some conditions for unsolvability is just to remove this complementarity. Then it means that we obtain condition which is not equivalent, but it is just the sufficient condition for unsolvability. And because we have now only the system of equations with non-negative variables, everything is nice and linear. And just for convenience, we can use the Farkas lemma to obtain the dual system. And at the end of the day, we have these sufficient conditions for unsolvability. So the sufficient condition claims if this system of linear equations or inequalities, which is the dual of this one, just by Farkas lemma. So if it is solvable, it means that the AVE system is unsolvable. So this is one condition for unsolvability. I will present you one more because I like it. You will see why. Another sufficient condition for unsolvability is the following one. If the spectral radius of the absolute value of A is less than 1, which is easy to check, and this vector, which is also easy to calculate, is not non-negative, it means there is one entry which is strictly negative. So in this case, the AVE system is unsolvable. And why I like it? Because it is the consequence of the following lemma, which says, under this assumption, we have this bound for all the solutions. So far, when I presented the methods for solving AVE, I just showed you some methods that converge to some of the solutions, but this gives us the bounds for all the solutions. So this lemma can be used to bound all the solutions together. And how? Here we have that every solution must satisfy in the absolute value this inequality. So this gives us the bound for the absolute value of all the solutions. So this is quite a useful technique. Of course, it is just the bound. It needn't be tight, but in some cases it can be bound. It can be tight, and it can help to solve the problem or find all the solutions. And from this lemma, the theorem follows quite easily because if this right-hand side is not non-negative, so there is one negative element. So in this case, there cannot be any solution because the absolute value cannot be negative. So this is quite easy to obtain this sufficient condition for unsolvability. I have also a brief idea of the proof because it's very, very simple, elementary. Because if we rewrite the system of absolute value equations in this form, and we bound the right-hand side from above by taking the absolute value and the triangle inequality, so we obtain this inequality. We rewrite it in this form, and now the crucial point is that the assumption gives us that this matrix has a non-negative inverse. So we can multiply it by the inverse, and the inequality will not change. This is important because otherwise we cannot multiply it by the matrix because the inequality would be violated. But this is not the case because we know that the matrix is non-negative. And here is the idea. the matrix has a non-negative inverse because it cannot be rewritten by using the von Neumann series theorem by this infinite series of the powers of the absolute value of A. And of course, the absolute value is non-negative, which means that also the result, the sum is non-negative. So just by using this von Neumann series theorem, we have as a consequence this result. So these were some conditions for unsolvability, and the very last thing I want to share on 1 or 2 slides is the relation to interval analysis. We already observed some relation to interval analysis because I presented you the result that about the unique solvability, and that the unique solvability is characterized by regularity of an interval matrix. But this is not the only relation to interval analysis. There are much more connections between these two areas. So just to formulate some of the results, so I will denote the interval matrix as usually by this lower and upper bound. Or equivalently, I can use the center matrix AC and the radius matrix A delta. Of course, the radius matrix is always non-negative because it's the matrix of radii which are non-negative. So this is the interval matrix, and interval system is just the system in which we have the interval matrix and interval right-hand side vector B. And the solution set, the standard solution set of this interval system is defined as the union of all solutions of all realizations, which means that the solution is any vector that satisfies a system of equations for some selection of matrix A from the interval matrix and for some selection of the right-hand side vector B from the interval right-hand side vector. And how the solution set look like and is characterized? So it is characterized by the Etley-Prager theorem, one of the early results in the interval analysis. So the solution set is characterized by this system of absolute value inequalities. So it is not an equation, it is inequality, but you can see that they are absolute values. So you can see the connection to our problem. And geometrically, it looks quite similar to our problem because in each orthant, the solution set forms a convex polyhedron. But if we take the union over all orthants, then the solution set is in general not convex. Here you have one example of the solution set which is connected. It can be also disconnected, but in this case it is connected but not convex. But it is convex in any orthant. In the positive orthant, negative orthant, in each orthant it is convex polyhedron. And you can see that the solution set has this star-looking shape. This is not by chance because it can be shown if the matrix is regular. So in this case, the solution set is connected and it has always this shape. And if we want to compute this shape and to somehow work with it, so we need to compute this peaks of the star. And how to compute them? So for this case, we have a very nice result by Ron, which was my great teacher, and he introduced me to this area, and he showed that the convex hull of the solution set is the convex hull of a finite number of solutions of vectors, and the solution XS is the unique solution of this absolute value system of equations. So, which means that the solutions, that the convex hull of the solution set, it means if you take the convex hull of this solution set. Oh, sorry, oops, I just skipped somewhere else. Okay. So we have this convex hull of the solution set. So we need to compute these vertices, and the theorem gives us the characterization of these vertices, and they are just the solutions of this absolute value equation system. So we need to compute this absolute value equation system, and it is basically of this form. So this is another relation of interval analysis and the absolute value equation problem. By the way, Ron also designed his own method how to solve this absolute value equation system. He called it sign accord algorithm because he just iterated and changed the sign of the solution. every iteration he changed only one sign of the vector of the solution. So that's why he called it sign algorithm, but I have no time to go into details. So to conclude my presentation, so I just wanted to share with you that this is quite easy to formulate but hard to solve area. It is quite a recent discipline, and there are many interesting results and also many interesting open problems to solve. Just to underline this, so you can see that the absolute value equations and absolute value programming became one term in the new edition of the Encyclopedia of Optimization, and maybe more importantly, we wrote with my colleagues some overview, some survey paper, which was published in the Computational Optimization and Applications, so it will appear quite soon. So if you want to see more details or to have the overview on the problem, so you can just check this paper, and you will get into the details of this stuff. So this is all from my side, and of course I'm open to questions, so you can ask whatever you wish.
So, thank you very much, Professor Milan Hladik, for your nice presentation about on the interval optimization. Now, any questions from the audiences? From both offline and online? Any questions from the audiences, please? I think no. So I have a small question to you. Did you consider the complexity, computational complexity of your problem when you apply your approach?
As I mentioned at the beginning, so many problems related to AV are NP-hard. So it is NP-hard to determine if there is at least one solution. It is NP-hard. Even if we know that it is solvable, it is NP-hard to check if there are more than one solution. So many results in this area are NP-hard, and they are proved to be NP-hard. But of course, there are also some problems in this area which are easy to solve. If you remember when I spoke about this non-negativity, so the non-negativity of the solutions, this is the case, one of the few cases which are easy to check.
Okay, so thank you very much. So any more questions from? No. So from the organizing committee of this international conference, it is our immense pleasure that we have a good speaker like you in this conference. Although in future we have a plan to invite you in the college or also university, but right now it is enough for us that you have already delivered your lecture through online. And the participants, those are here in the audience, they are very much interested to listen to your lecture. Thank you very much, Professor Milan. Thank you.
Thank you very much for the invitation.
Okay, thank you.
Thanks.
Thank you so much, sir, for your enlightening and thought-provoking lecture. Thank you. Thanks again, sir.
Thank you, sir. Hello. So we will invite you for later our conference.
On offline mode.
Okay, it will be a pleasure for me.
Okay, okay. Thank you, sir, for your kind presentation.
Thank you very much.
We now break from lunch 1:15 to 15 p.m. Then we come back in our next session. Thank you everyone for listening the lectures. Thank you, sir.
Thanks. Goodbye.
Goodbye, sir.
Thank you.
Hope you soon again.
Bye. So we will see you later.
See you.
navigating uncertainty towards a robust pension fund management framework. Sir, Professor William Weber is an eminent professor of engineering management of Poznan University of Technology, Poznan, Poland. His innovative research interest includes mathematics, statistics, operation research, data science, machine learning, artificial intelligence, etc. Actually, his research area is very wide range. He is an IFORS fellow. He has many research articles. The number of his research publications is 1521. His groundbreaking work in his field has earned globally recognition. We are truly honored to have such an esteemed expert with us today. Please join me in warmly welcomes Professor Weber. We are very glad to have you, sir, in our conference. Sir.
Thank you so much. I'm very happy to be online with you. And thank you for your kind introduction. And I also see my close friend, my brother, Professor Roy.
Good afternoon, Professor.
Hello, my scholar and close friend, Professor Roy.
So how are
Good to
you?
see you.
How are you in Indonesia?
I am very happy to be with you today online. And as you know, I am also at the same time participating at events in Indonesia, as you indicate. And I was very happy that my host family here, my hosts, made it possible to have a free slot. So I'm very grateful, and they gave me a very beautiful room with high-speed internet. So I got high-speed internet, Professor Roy,
Yes.
to meet you and your best friends in beautiful West Bengal, which is close to our heart, as you all know. You are close to, you all, Professor Roy, and the whole scientific school and university are so close to our heart. Happy and very deeply honored to be with you.
Thank you very much. Right now you are the international figure. So I cannot say much more about you. Everyone can put your name in Google search engine and get so many informations about you. Okay, so all audience and here the offline and online, they are waiting for your fruitful lecture right now. Thank you, Professor, very much.
Yeah. Thank you so much, Professor Roy.
Yeah.
Professor Best Friends. We call people like you best friends, is right?
Yeah.
And when I mention India and the Indian people to be so good to me, this helped me in my life.
Thank
Not
you.
only to have a good feeling, but it was existential. The helping hand of people of India, the Republic of India, was existential for my life and will never be forgotten. So thank you so much. And today I will speak on a subject which is not the same as I published a lot with a group of Professor Roy. It will be different. Okay, so let me see whether I can share screen. One moment. Share screen. Please give me a moment. So share. And I will share. One moment, please.
You see the bottom of this line, there is an arrow.
Yeah. I will do so. Share, but I have to click. And it's not shown. Please, one moment, because I should activate my PDF. I click the PDF, but it's not shown. So one moment, I will try again. So where is my PDF? Application window. Aha, here we go.
Yes.
So now
Now it is visible. Now it is visible.
Okay. So
Make
show
it larger.
my screen anyway. Show my screen anyway, and let's go. Is it better so? It's better. Can you see it all?
Yeah.
Okay.
Is it possible to make it larger?
Let's try. Let's try, Prof. Let's try. One moment, please. Maybe I have to. One moment. Is better?
Yeah. Right now it is better.
It's much better?
Yeah.
Okay, so Professor Roy, Professor Best Friends. So one more time, Professor Roy, also to you particularly. Oh, I spoke to the whole Indian nation, and now I speak to you personally. You have always been very good to me. Whenever we met for the first time on a boat in Shanghai at a beautiful conference, and we liked each other very much and got into sympathy and collaboration, you have been wonderfully generous to me and wonderfully positive to me on a daily basis. I think we meet nearly on a daily basis. And just today, I said wonderful things about you to my friends from Indonesia. To your friend, Professor Herman, I said how wonderful you are. And I mentioned you to some other people. So maybe in future you will collaborate with these scholars as well as you do with scholars from Europe and the whole over the world. Professor Roy. Now, the topic of my talk is a new study. It's not mainly by me. I will give you the main players soon, but by a scientific team consisting of scholars from Greece and Poland and myself. Some of you know and see it by my name. I'm a German. I have a German name from German-speaking part of the world, and I work with people from Greece and Poland, and we have made this study possible. And these are the persons. Main author, also of the slides themselves, is Professor Yannis Baltas. He's academic teacher, Athanasios Yannakopoulos, Professor Czepansky, Dr. Koledziejczyk, and Dr. Dopiela from Poland. They are our scholars. The latter three are our scholars from the area of pension fund systems. Pension fund systems. Now, Ernest Hemingway wrote, "The world breaks everyone. It breaks everyone." You know, he had such a philosophy. And afterward, some are strong at the broken place. This goes to show life is full of risk, but also life is full of chance. And we are facing with uncertainty. And our uncertainty is in a domain which is called finance. But it's not any kind of finance, it's pension fund systems, which is, so to speak, on the interface between finance and social security. That's what we call pension fund systems. Now, the role of stochastic models in many fields, such as insurance, economics, and finance, systems exhibit behavior influenced by randomness. We know this. And Professor Roy, you address it by the help, for example, of fuzzy logic and other tools in your scientific papers. The randomness may arise from incomplete data, from model assumptions, and external factors. Stochastic models are essential for capturing the randomness in these systems. So, in our case, we will choose stochastic models. This is what I always propagate. These are, so to speak, at the end of the road when it comes to include more uncertainty. And Professor Roy, in a number of his papers, mentions about stochastic extensions in the outlook parts of his papers. The crucial question, how to decide when we face uncertainty concerning the exact stochastic model that describes the evolution of the system under consideration. Point is, we usually do not know the exact model. So we have to have what we call in robust optimization, what Professor Roy knows very well and his team, when we have an extended notion of an uncertainty set. Our uncertainty set will not be a box or an ellipsoid or so of points, of higher dimensional points, of parameter values, but rather this will be uncertainty sets in the world of distribution, of probability distribution. Saving for retirement. This is a very important issue. It's all the more true since in countries like many Europeans, like Germany, for example, we are facing with issues in the age pyramid. In large parts of India, you have many young people, and of course many old, but relatively few compared to the young people, old people. But in Europe, it's often the opposite. We have many old people and a few young, and that gives us a problem. How can life in future, when we are old, if we reach an old age, I'm already a little old, 65, how can our life be financed if we have a rolling system by the young people? So the problem of optimal management of assets accumulated in pension funds under risk and uncertainty is a matter of fundamental importance, both in the theoretical and the practical dimension. You know, in our countries like Europe, we have to pay while working money into a pension fund. And the pension fund is a company, or is, let me say, run through a company on behalf of a state, which collects all the money. Ours, which we, through our employers, send into those pension funds, and then the money is invested into the capital market, because the money is not just only put on a bank account. Money works. So these are decisions to be made. Essentially, a pension fund scheme constitutes an independent legal entity that represents accumulated wealth stemming from pooled contributions of its members. The wealth is to be invested over a long period of time to provide its members with retirement benefits. So all the money which is put through us, to be more precise, our companies or institutions that employ us, all the money put in the pool, and what we, through this company who is in charge of sending us the money, retirement, puts also on the stock market. So they have to economize very well. Such companies must invest their money very responsibly. This shows us here how in our countries, especially the West or like US, the pension fund assets grew in the last around 14 years. Those are papers that we benefited from, authors from Spain, from all parts of the world, but also Poland. So Professor Czepansky and his team belong to the leaders in pension fund systems in Poland, including questions like longevity. Actually, we have made the paper, the Greek professors, myself, and the Polish friends, and published it in one of the best journals in OR. Professor Roy knows the journal very, very well. It's called EJOR. So we have published, and now we have submitted a new paper. And we try to make the new paper more realistic, including aspects of longevity and others. I will come to this. Okay, so these were our studies, Professor Baltas and his friends, so these are papers of mine and my friends, other scholars like Reza Lotfi and others, also with me. And so here we go. So this is our paper now submitted to EJOR. Let's see what comes out. Imagine you are making the decision about the future, investing, managing risk, and setting policy. So we have to have a reference model, but we are not sure about the reference model. So either we are setting the parametric model a little bit broader in terms of the uncertainty set or much broader? And this depends on our risk friendliness. In modeling, are we risk friendly or risk averse? Should our uncertainty set be bigger or should our uncertainty set be smaller? So these are issues we have to address, and the uncertainty set, so to speak, grows around a reference model. Do we take the reference model or put it parametrically a little broader or much broader? So these are issues to be addressed. A powerful idea: incorporate model uncertainty into decision making. This means make the decision making including the decision about uncertainty. This means modeling of uncertainty, modeling in general is hybridized with the decision making, with the financial mathematics of this pension fund scheme. So this is what we do. We hybridize, we match modeling with decision making. That's what we do. Look here, the red point, this is our reference model. And we can grow to any direction because we are not sure if this circle or this represents to us our uncertainty set, and we want to robustify. How big should we make it? And inside of a once decided uncertainty set, how far do we go? Do we stay at the red point itself, or do we embark to robustify more? If we are risk averse, maybe we stay at the red point. We stay at the red point. I will come to this a little later. Okay, so one paper has been written and another one has been submitted to IJUA. The design of the pension fund scheme. At the time of retirement, which is time zero, L0, L0 lives enter a life assurance. So at that time, it's time zero, the reaching of retirement age, depending maybe, let's say 65 or 67. Enter the life assurance contract, which is similar to an insurance, but not the same, with the same insurance firm by paying upfront the amount XC. And this money is to be multiplied with the number of people. So this is the number of people, L0, the money and the number of people. This money, LX sub 0, is then collected by the fund manager of the insurance firm to a portfolio savings account and is to be invested optimally in the market, capital market, offering three opportunities. It's a bond. You know, some of you like the criminal films. Bond. My name is James Bond. Like the Bank of England. Very, very safe. My name is Bond. James Bond. The Bank of England. Inflation adjusted bond. Inflation adjusted. Why? Because such investments during the life of retirement, those ages, let's say 20 years, just to give a number, the money is getting less worthy. There's inflation. Over 20 years, money loses generally its weight to some amount. So we have to adjust the bond with inflation. And that makes this product risky because of the risk, the uncertainty which is involved in the inflation itself. The another risky asset, which is stock index. So then it's the classical way how, for instance, through Wiener processes, let's say Brownian motions, the uncertainty enters into the financial dynamics. And a simple bank account, which is truly a bond. This is like you bring your money to the best and safest bank in India, let's say, for example. So And so there are some examples: inflation in the US, SP 500 financial index, and a secure overnight financial rate. This is the US-based fund manager. Now, we have also to take into account all kinds of premia and benefits. Premia and benefits. And we assume this to be positive. This is assumed to be dependent on the performance of the fund portfolio. The fund portfolio can do successfully or less successfully. And to express that in time, we include such a variable Q of t. If the number of the member is alive, the member in the pension fund system, a saver and a pensioner, at the end of the investment period, which is capital T, he is promised this amount of payment. This amount of payment, which is the difference between the compounded by an interest rate of R sub F, this compound factor times the number X sub C, which I told you, minus a strike price times the time T itself, the time between time 0 and time capital T, it's capital T itself. And this R sub F should be bigger than the nominal interest rate, because it should be attractive. Interest rates should be attractive, and in our case, it should be attractive when compared to what we, for example, would get just through a bond, which is the interest rate in the market. And K is, as I said, the kind of a strike price. So we need this positivity assumption here in order to ensure that we are liquid. If we are runners of such a pension fund portfolio company, insurance, let's say, company, then it should be positive. Otherwise, we could be illiquid. And such a company who serves our nation, our population, should be liquid. If there is illiquidity, there is a problem. And then we are using the Gompertz law of dying, of morbidity, to describe the force of mortality, mortality intensity. We always have intensity terms in all kinds of situations of reliability. And we have here the pension fund system, which also has to function in a reliable form. So this is calibrated to a real mortality table, like US total, in the case of US total population. We have mobility tables. Some of you are from insurance mathematics, life insurance, and you know these details very well. At the end of the life assurance contract, the fund manager is obliged to compensate the survivors by the by the amount of A0, and sometimes the estimated value of A0 is the estimated population of survivors at time capital T times A0. So this is the number of people who survived, estimated, because we don't know it, times A0. Expected lives times compensation. In this direction, this manager sets a desired target to be reached at the end of the trading interval. It equals A hat, and then we take a buffer. We take a theta, which is a buffer, so to have a number which is bigger than 1. So we leave some extra buffer when compared to factor 1 times the estimated A0, A hat 0. And so this number, which is the capital process, Y of capital T minus A hat, this should be maximized in terms of its utility. So in all contexts of modern economics, unless it's the modeling is based on risk, but if it's on utility, we want to have the biggest utility between the difference of what this number is, what has to be provided, and on the one side, this has to be provided to the savers, and this one which is on the capital market. But you will see this number is not the capital process itself. It's an indexed capital process, an indexed one, indexed in terms of inflation. So this should be positive. We don't want an illiquidity here. It should be positive, and it should be attractive. It should be attractive for the company. Otherwise, it's penalized. Otherwise, we have to penalize if Y is smaller than A hat. So here we go. As I said, Y is an indexed expression of X. X is what we get in terms of portfolio optimization on the capital market through the three products which we have. I mentioned them. I will re-mention them. But divided through the inflation process, because it's, so to speak, money relative to inflation. So it's a cleaned, it's an indexed capital process. So, and then we have here this logarithmic derivative of Y, and this is here our term, and we plot in our financial dynamics. The financial dynamics of our three products, whether it's the bond, the plain bond, the inflation indexed bond, or whether it's the stock market share. So these are now put in, and of course we are using in the further work, the financial mathematics work, the calculus, which we call financial calculus, which is a generalized version of the calculus we all know from Newton and Leibniz, but with all the chain rule and so forth, with all these adopted to the stochastic and dynamic context of what we see here, which is stochastic calculus, stochastic dynamics. So this is our initial value, small y, and this is here the technical term where we put all these things together. Actually, you can consider this here to be expressing our premia, our incentives, our different interest rates. So these are all very meaningful and interpretable terms, interpretable for the persons of finance and economics. Given the long-term nature of the pension fund, it is natural for the fund manager to choose his or her decision robustly. Robust. Because we have uncertainty, and the conservative way of uncertainty management is robust optimization. It's in our case robust optimal control, stochastic optimal control. One way to introduce model uncertainty is through the stochastic processes W and B. So one stochastic process is coming from the inflation process. The inflation process has its own Brownian motion. And we have from the stock market the Brownian motion, which is directly related to the financial asset and its randomness. A Brownian motion is, so to speak, a standardized form of a random fluctuation according to normal distribution. So there exists a true probability law associated with W and B, but the fund manager is unaware. It's unaware. So it exists in an uncertainty set of distribution, which makes a Brownian motion be a Brownian motion. A Brownian motion is a Brownian motion not by itself, but in reference to a probability measure. The probability measure, which is supposed, makes a Brownian motion to be a Brownian motion or not. So, and if we perturb a Brownian motion, the Wiener process Brownian motion need not be a Brownian motion anymore, and vice versa. So there's a coupling. The fund manager only has an estimated idea of the law, which may be different from reality. So we have to make a robust decision. And how robust? This kind of tuning is in our hands. He or she considers a family of alternative models, and the goal is to make decisions that perform well under the worst case among these possible alternatives. This is always the case. And we are speaking about here, it can be considered as an information criterion about a Kullback-Leibler entropy or information. So that is the term which is sometimes used and you find in literature. So what we have here, you can also call it Tikhonov regularization. Tikhonov regularization or rich regression, but adjusted to the very particular situation. So this here is what we try to make big. This is what we try to make big. And this is our entropy. This is our energy term, however you like to call it. And this is showing you how big. So these are, so to speak, the sizes of the uncertainty sets of our two Brownian motions, S and I. This is the stock, S is like stock, and I is like inflation indexed bond. So this kind of uncertainty, and either we make lambda big or we make lambda small. That's the point. And this depends, because beta is, so to speak, a parameter of risk aversion. This means, look, dear friends, we want to make this big here. We want to make this big, but we want independence of gamma, of this gamma. We want to make or lambda, dependent on lambda, we want to make this term small. So to make this small, now if beta becomes close to zero, and the nominator is positive, a small beta close to zero makes this term very huge. But we want this term to be very small. This means we must compensate these growths by making the lambdas close to zero. A small close to zero beta is compensated by lambdas which are close to zero. So this is our thinking. This means when beta is very close, we must make our lambda close to zero, and lambda close to zero means we stay close to our reference model, because we don't deviate. We don't deviate much, very little, from the reference model around which the uncertainty set evolves. I hope it's clear. You can also study my slides and you will understand it easily. So one more time, you can call it relaxation. We have to become relaxed, but not too relaxed. And you can consider this here as a game. Sub, inf, max, min. So this is a max, min, a settled point problem. It's a settled point problem. It's a game. This is a game. And this is our financial dynamics, stochastic dynamics. And the elements are beta tildes, p tildes, and w tildes. And these are the Brownian motions associated to the elements of our uncertainty set, which are uncertainty sets in the world of probability distributions. Now, we have a player A, so to speak, and this is the fund manager. So the fund manager who chooses the best portfolio decision. A pi and B are the best decisions, and one is about the activity on the stock market, and the other one is about the bond, especially the indexed bond. And the difference between pi plus b from 1 is for the stock market, for example. Okay, and the other one is the player B, a fictitious agent. We can consider this like the environment or the nature. This is the nature of uncertainty. This is who chooses the model Q. So the model Q is chosen by the second player, like in chess, 2 players. And he decides or she decides about the lambdas. I hope you like it. I think it's a beautiful interpretation of our problem in terms of game theory. And you know, Professor Shankar Kumar Roy is working with his team also by the use of game theory. It's one of his methodologies, game theory. Professor Shankar Kumar Roy. Okay, so we have here player A, player B, and we can find optimal solutions. We can find optimal solutions for the portfolio model and also for the modeling problem, the uncertainty modeling problem. I hope you like it. And we can solve it further, for example, to find the value function. We can continue our solving the problem, for example, by discretization in Monte Carlo simulation. I don't tell you the details. We have, for example, here also our Gompertz law, which is not exactly like a line. And this shows us the lives remaining in the pension portfolio at each instant of time according to a Gompertz law. Maybe I should hide this here. So this is the Gompertz law. It's an exponential function representing mortality. Now, dear friends, look here. We have 3 curves. One curve is this dark curve. This is the stock in time. And then it's the light curve, which is the bank account. The light curve is a bank account. And then we have one intermediate, but it's running the opposite way. This line runs in the opposite direction. So this line is for the indexed bond. The indexed bond. Okay? The indexed bond. And now, we look at different values. We let beta go up. We let beta go up. And then beta goes up. Beta, please remember, was our risk aversion. In modeling sense, our risk aversion. So then you see, when beta goes up, this curve goes up. This curve goes up. Because it means with increasing beta, our indexed bond becomes more attractive. Our indexed bond becomes more attractive. More risk aversion means we stay close to our given model, and then our attractivity of our indexed bond when compared to the 2 other financial products has increased. And the other thing is, the other point is that we let now our initial capital, our initial indexed capital go up, and then we have the same effect. Look here, here this is our, this line is our bond, this line is our bond, and the bond goes up, when this initial capital grows. That means when we have more money, we can invest more, we can do more. Then this bond, which is a kind of a compromise between a stock, which is often very risky, and a supposedly non-risky bank account asset. So this compromise asset, the inflation indexed bond, has become very attractive. So it was a very good idea of my friends to propose this issue, to propose the inflation index bond, because it turns out to be very attractive. Now, what we do in our second model now, in our second study, is a multi-period framework for optimal management of the proposed pension scheme, accounting for its dynamic and long-term nature. So multi-period, not one period, multi-period. And then we have stratified age group, stratified age groups. So it's not homogeneous. The age group is not just the homogeneous population, but it's stratified, where members are segmented by age cohorts, each governed by its own stochastic mortality model. Because people are not people, they are different, and according to the age cohort, the mortality is not the same. And we have a novel mortality learning mechanism, which means we have a rolling system that enables the system to update and adapt mortality expectations over the time. So the more we learn about mortality and the older the people grow, the more we have to see the reality and have to update expectation through the intermediate observations. So, and the realistic model accounting for two different sources of uncertainty. Accounting for two different sources of uncertainty, which is the financial market and the mortality. Both are sources of uncertainty. Not only the finance, the economy, but also the mortality, which was previously not really looked at in our previous EJOR paper. Okay, so the members may join the scheme anytime by paying upfront an entrance fee. The wealth is invested. I don't need to repeat it all. Upon joining the scheme, members are categorized into distinct age groups. Members are allowed to exit the scheme at any time. The beneficiaries of the members are who pass away. I mean, the people who inherit are entitled to compensation, and the surviving members are entitled to benefit payments. So there's always a benefit, whether these are the family members, let's say the people who have inheritance, and also the people who survived. And the insurance company keeps a constant amount per year in order to cover trading costs and operation fees. So this is our problem. It's the same like above, but we changed. From sub-inf, we have now inf-sub. It's only a change of the perspective. And now we have no utility. We have here an approximation problem. You see, this is not just, let me say, a classical utility. It's now particularly an approximation problem to make the difference between this target A sub t and the capital process according to the distribution as small as possible. So this is a different approach, and that's why we have a minus here. Previously it was a plus. Okay, and here you see the rolling system which Professor Balkas and his friends invested. This means for different time points, here for example 4, can be more, we have always to make an update. So we have here the update of A1 at time capital T1. We update, we have A2, which is, so to speak, the money who has to be available, the liquidity who has not to be underwent in height through the capital process. So this has to be updated. And here our mortality terms about the people at the time to live, they are updated. So we have a rolling system of expected mortality and of the expected liability of money which has to be provided through the pension fund system towards the people who have a right to get the money, whether it's the survivors or their beneficiaries. Okay, so there are 3 groups. One contains ages 50 to 53, 54 to 57, 58 to 51. And you see the number of lives. 2,000, 2,500, 3,000 lives. We consider 4 yearly operation periods. The first period starts in 2024. We consider 3 different models for mortality named Ornstein, Uhlenbeck, Wasicek, and CIR. Models are estimated with the OLS method. Okay, so Ornstein Uhlenbeck seems to be the best fitting model for each case. So that's what we assumed, or what we found out. So these are snippets, means small segments, small yearly figures, numerical figures of these cohorts. Okay, I don't need to show you all. I will finish. I will finish. Professor, I will finish.
स्वास्थ्य कैसा है?
Sorry?
आपका स्वास्थ्य कैसा है? सब जानकारी हुई, स्वास्थ्य आप स्वस्थ हो गए कुछ दिनों पहले, अब बढ़िया
Sorry, it's a bit loud.
स्वास्थ्य बेहतर
Just finish.
है।
I will finish. Please be quiet. Please don't be speak now. Let me just finish, please. I do it quickly. So we have here. Look at this. We find the best fittings to cast the mortality model. We found the value at risk, which is our risk measure. We adjust according to this risk management, according to according to value at risk. We adjust if needed, and we find the upper bound for expected death and the target. So this is our rolling system. So we have here an optimal wealth process. Sorry, an optimal wealth process for the first, for random optimal wealth process for the first period, for the second and third period. This is the mean optimal paths for period 1, period 2, and period 3. And then these are our snippets for the overall performance, initial wealths, expected terminal wealths, and the target. These are the overall performance of the pension fund portfolio. So this is much more refined than in our previous study. This is now the good thing which means basically my scholars who did all this hard work found out. So, dear friends, let me say, we studied, first of all, when I moved to Poland, and we started to work with the Polish people and our scholars from Greece. We had a little simplified, in fact, complicated enough model, but it was not fully realistic. To make it a little more realistic, we made adjustments through this rolling system in terms of mortality and in terms of liability, let me say, liquidity needs, expected liquidity needs, which have to be satisfied in the pension fund system. So I thank you very much for your kind interest. I hope it did not take too much long, and I hope you liked it a little. And if you want, I think Professor Roy has my slides. Otherwise, I can send him, and he can distribute those slides to you. And you can work with my Greek and Polish scholars on it in future. Thank you very much.
So thank you very much, Professor Weber, for your nice and thoughtful talk. All the audiences are already enriched, and we are running late. That is why, without any questions, I must again thank you, Professor Weber.
Okay. Bye-bye, dear friends. And please come to Euro conferences and IFOS conferences.
Of course,
Thank you
try
very
my
much.
best to meet you at Euro. Thank
Bye-bye,
you.
Professor.
Thank you.
Bye-bye.
Thank you
God
very
bless
much. Bye.
It's okay. Thank you. So here we have ended our invited lecture session. Then we will go to our parallel session, which will be paper presentation. So thank you everyone for this, for joining in this event. Thank you everyone. There are two links in the time schedule, two parallel session, Group A and Group B. I think Group B, the link of Group B is activated. The participants of the Group B can join there, and the participants of Group B can try to join Group A from this time. The ongoing lecture is ended, so they can join. Thank you everyone.